Hello everyone, welcome to the lecture 25, the Mohr-Coulomb strength criteria. Today we're going to talk about the Mohr-Coulomb criteria, which is a strength criteria that we use in the soil mechanics. And the second topic is about the direct shear test. So these are the two topics that we will talk about today. Let's begin with the handout 20. Yeah. So Coulomb friction law is, I think that you will be very familiar with this physical concept that you learn from the high school physics. So if there's a mass, the object having a mass m, then it will have a normal force acting on the surface, which is m times g. And to move and to displace this object with the force T, then you have to increase the T to the to this amount. So here the T force to displace an object is C plus mu times N. Mu is the normal force by the weight of this object, and mu is coefficient of friction. So then if we convert this one into a soil, then when we have soil mass like this, then we want to shear it with the potential plane of this. So we will have a force. And if we divide it by the area, so this should be the T, and there's an N. And we can change it to a stress term. It's going to be the tau, the shear stress, is equal to C plus sigma n times phi. So phi tangent phi is correlated to this coefficient of friction. And here phi, we call it the friction angle or angle of internal friction. And besides that, you have also the cohesion term. So if there's some bonding force, adhesion between the surface and the object, it will be expressed in this term C, cohesion force between the surface and the object. And you can also we can adopt this concept in the Mohr-Coulomb criteria using the same symbol C, and we call it apparent cohesion or cohesion intercept. So you can see that this shear strength tau is function of C, the cohesion intercept, and the sigma n, which is the normal stress. So here the sigma n will be n over A. And the tangent phi, the friction angle. So if you plot it in the sigma versus tau space, then it will have a y-intercept C and inclination angle phi. And so you can see that the shear strength tau is stress dependent. As the normal stress increases, tau f, the shear strength, increases. For sand, the C is almost zero, so it will be something like this. And when the C, for the clay soil or the silty soil, they have the cohesion intercept larger than 0. Mostly, friction angle of the sand is greater than the friction angle of clay. And failure plane can be different depending on the stress condition. So use the Mohr circles to find the stress state at the plane of shear failure. So this means that say that if you have soil mass that's under principal stress sigma 1 and sigma 3, then let's imagine here tau theta and the sigma theta, the normal stress on this plane, will be different from this stress. So you have tau and sigma, right? So no, as the plane angle differs, you can define like infinite number of planes of interest, and depending on that plane, the stress condition on that plane will be different. So if the stress here at a certain plane is greater than this tau f strength, then the failure will occur. So to find the failure condition, we have to use the Mohr circle for a specific plane of interest. Okay, the next page. So failure plane in Mohr-Coulomb criteria. When the Mohr circle is tangent to the failure envelope, then failure occurs in the soil. That means that we have a slope here, and then we are building a foundation here. So the sigma, delta sigma, the total stress will increase over time as you go first story or the second story, third story, as you go higher and higher. So then initially the stress state here, sigma 1 and sigma 3 was here, were applied on this soil mass, and this will make a Mohr circle, the small circle like here, sigma 1 and sigma 3, crossing at there. And as the delta sigma increases, right, then, and while the sigma 3 stays constant, sigma 1 will increase. So then the circle gets bigger and bigger, and at some point it's gonna touch. Right? It's gonna touch the this shear failure envelope. So this shear failure envelope is defined as C plus normal stress tangent V. Right? So when the Mohr circle touches the shear failure envelope here, this one, the red line, we call it failure. We assume that the failure occurs. So then, where the failure occurs? So this is the point that the stress state causing the failure in the soil mass. So then this sigma theta and tau theta, or tau f, so this becomes greater than the tau f, and the failure occurs, shear failure. So stress state at this point is sigma theta times tau theta. Okay. So then where the failure plane will be? So the inclination of the failure plane. Can we find the alpha f from this Mohr-Coulomb criteria? So Coulomb frictional criteria and the Mohr circle. What's the alpha f? That's the question here. So then if this is the stress state given, we can find the pole. Where is the original plane? Because the sigma 1 is applied on the horizontal plane, so if you plot it, this will be the OP, and you can double check with the sigma 3. Sigma 3 is applied on the vertical plane, so then intersection with the Mohr-circle will be OP, right? So then you can draw the failure plane here. That's from OP to the tangent point here. And this line will be to this line will be parallel to the failure plane. So then we can, from the pole method, this angle will tell us the angle of the inclination angle of the failure plane, alpha f. So then how can we find the alpha f? Using some trigonometric relation or simple geometry. This is the center. Then with the right angle, and you will have the same length, the side length for this triangle. Right? And you draw a line with the right angle from the center vertically, then when this is the friction angle, this is friction angle. Right? So then if we have this triangle, so if you bring this triangle and zoom in, then this will be, here's phi, so this will be 90 minus phi, and this, here is alpha angle, alpha f. So we know the angle of these three corners inside. 2 alpha f plus 90 minus phi will be 180 degree. So from that, alpha f will be 45 plus phi over 2. So for a soil with a specific value of the phi, the friction angle, and friction angle is the soil property, so it will have a unique one value. When you know the friction angle of the soil, then by the compression, by the definition, using this straight line of the Mohr-Coulomb shear failure criteria, we can estimate, predict the failure plane inclination, alpha f. And this is very important for the follow-up analysis in this class. Okay. And then in the next page, we can estimate the factor of safety for this given potential failure plane. And factor of safety, so this is the stress state with this small Mohr-circle, and right now this Mohr-circle is not touching the shear failure envelope, right? So it is, we know that it is safe. Then we know that the potential failure plane angle, alpha f, and this is the shear stress at this plane, right? So you have soil mass with the alpha f is will be the tau theta, and here is the tau theta, no, tau f. And if you compare for the given, this is a sigma f of this failure plane. If we know the sigma f, then we know the shear strength available for a given normal stress for on this plane. Then we can compare this tau ff, which is the shear strength, to the shear stress on that potential failure plane. So here the factor of safety for this stress condition is given by the shear strength over mobilized shear stress on the potential failure plane, which is in short 45 plus phi over 2 plane. So yeah, at failure, if you go down, it shows the failure case. This is the alpha f, which is 45 plus phi over 2. And then shear stress on the failure plane will be the same with this tau ff. Okay. So then what's the most weakest plane? That's the plane with the inclination angle of 45 plus phi over 2. Angle of the plane that has the maximum shear stress. What's the angle of plane that has the maximum shear stress? In this Mohr circle, which one has the maximum shear stress? Maximum shear stress is at here, right? At the peak of this circle, at the center, right? And this will be the tau max. So then from the OP, so here is the OP, where this plane locates, if I use the different color, this plane, on this plane, we will have a tau max. And the angle of this is 45 degrees. So the answer is 45 degrees. That means that in a soil mass, if the sigma 1 is applied here and sigma 3 is applied here, then 45 degree, the plane with the 45 degree inclination, you have the tau max, the maximum shear stress applied. But because the normal stress is very high, right? The normal stress is very high. So tau ff, the shear strength, is still greater than the tau max. But if you tilt it a little bit more in this angle, alpha f, tau f is the same with the tau ff. So you have the best or the most likelihood fail along this angle. Okay. And if you go next page, there are some useful relations to find the stress conditions at failure. This uses the trigonometric relations. So it's based on that the cosine and sine functions. And so be careful, this is the stress condition at failure. Okay. So when the strength criteria or the strength envelope, shear strength envelope is C plus sigma tangent phi, and the angle is tangent, the phi, the friction angle. Then we know that the center is sigma 1f plus sigma 3f over 2. And we can find the R too. R is sigma 1f minus sigma 3f over 2. So as shown in here, this is the radius of this Mohr circle. And then this is the cohesion intercept C, and we have the angle phi. And when you look at this triangle, we can use the trigonometric relation, right? So D is cotangent phi plus sigma 1f plus sigma 3f over 2. And here is the phi. So then the sine phi will be what? The sine phi will be D over R. So sigma 1 f minus sigma 3f over 2 over C times cotangent phi plus sigma 1 f plus sigma 3f over 2. So then if you simplify the equation here, then you get this one. If the C is 0 for the sand, then this equation becomes very simple because it goes to 0, right? So then you have only this one left. So the sine phi will be sigma 1f minus sigma 3f over sigma 1f plus sigma 3f. So just the principal stress difference over the sum of the principal stress. Okay, the last one. So using this, you can also derive the principal stress ratio at failure. So this one, sigma 1f over sigma 3f is 1 plus sine phi over 1 minus sine phi. Or you can express this one with the tangent square of 45 plus phi over 2. Okay, there are some examples that you can do it for yourself, and we're gonna review this problem together in the classroom. Okay, I guess this is the direct shear test. Today we'll talk about the direct shear test. So direct shear test, you have a shear box, and in shear box there are two boxes that's in two halves, so that separated each other, so that you can apply the shear force on the soil in the soil mass. And this shear box can can be a square shape or a rectangular shape, or it can be a circular. You can see that there's a loading cap that can apply and transfer the normal load, and the porous plate is at the top, and then you pour the soil inside. There's an upper box and the lower box. So between the upper box and the lower box, you can shear it. The unique characteristic of the direct shear test is that you're defining the failure plane beforehand. So predetermined failure plane. So in direct shear test, failure plane is horizontal. So, and that makes the calculation very easy and obtain the shear strength very easily. When you look at the picture here, it shows the direct shear testing apparatus, and it applies the normal force using this loading frame. And here, this one measures the normal load, the force N, the vertical force, and this one measures the vertical displacement. And while it's moving the bottom lower box using this motor, so this motor is pushing the lower box to a certain direction here, maybe to this direction, and then it's gonna be sheared, and during the shearing it measures the force using this load cell. So shear load T, and this measures the horizontal displacement. So in direct shear test, you need to know how much load you're applying in the normal direction, the vertically, and you need to monitor the vertical displacement and the horizontal displacement and the shear load. From that, you can obtain the shear strength. So this in the next page, it details the procedure. So place a sample inside the shear box, and then apply the normal load N, and then apply the shear load T. Yeah. And during that shearing, you have to measure the vertical displacement delta H, which is this one, whether this loading cavity is moving up and down during the shearing, and the horizontal displacement delta L, which is this one, and the shear force T. So then you can plot this kind of a graph. So first, here, let's say that you're performing 3 tests at different normal force, P1 and P2 and P3. So at P1, you apply the force, normal force, and then you're shearing, then you're measuring the T, and because you can calculate the A, if you divide the T with the area, then you can get the shear stress. And here the A is specimen area. Then as the delta is the displacement that you're measuring here. As the delta increases, shear stress increases, and then it can go down like this. So this will be the then peak shear stress before the failure. And you can perform and repeat the test with different P2, different normal stress. Then this becomes the peak shear stress before the failure, and then this one becomes the shear stress before the failure for the normal load of P3. And P1, P2, P3 will give you the sigma N1 and sigma N2 and sigma N3, and from that you can plot the peak shear stress versus the normal stress, right? And when you find the linear line connecting this dot, then the angle of this linear line will give you the friction angle. And the cohesion intercept in the y-axis. And on the other hand, meanwhile, you are measuring the vertical displacement, right? With the loading cavity going up and down. So then if you plot the delta H versus the shear displacement, as the volume expands or the loading cap goes up, then this means that the volume is expanding. If the volume goes, the loading cap goes down during the shearing, it means that the volume contracts. So this graph also tells you about the volume change during the shearing. And the volume expansion is called the dilation. Okay. So then what about the stress state? How the stress state changes during shearing. So initially, sigma n is applied, right, from the P through the loading cap, and you have a sigma h horizontal stress by this rigid wall of the shear box here. Right? So this wall provides the horizontal stress. Right? So this becomes the sigma 3 knot. So here we are assuming that there's no shear stress on this plane, the horizontal plane, before shearing, and also that there's no shear stress on this vertical plane. So sigma h becomes the minor principal stress, and sigma n becomes the major principal stress. So we can draw this kind of Mohr circle. Right? Sigma 3 knot and sigma 1 knot. And then the pole will be here. So in this failure plane, let's say that we are looking at the so this is the shear box. Inside we have soil, and this is the potential failure line, failure plane that we are looking at here. So then sigma n is applied here, and here sigma 3 knot, right? So then this will be the pole. What about at failure? When this shear box moved by this much, then here the soil mass is failed by the shear stress applied on the horizontal surface, and that's given here. So then is this plane still the principal plane? The definition of the principal plane is the plane that has no shear stress or zero shear stress. Now this plane, horizontal plane, has the shear stress of tau ff, so it's not anymore the principal plane. So then where will be the principal plane? Let's think about this one. So sigma n is p over a, and the tau f will be t over a. Right? So then you can plot, if we know the tau ff and the sigma n, that we know that at some point that's causing the failure in the failure envelope, on the failure envelope line. So in this failure envelope line, the failure stress, the stress at the failed condition will point here. Tau ff, no, sigma ff, comma tau ff. So then the Mohr circle should be in tangent to this Coulomb friction envelope, especially at this point. So you can draw Mohr circle using this one having some tangent. Right? Like this. So this will be the center. Then we know that this sigma ff, comma tau ff stress is applied on the horizontal plane. So if we plot the line to find the pole horizontally, then cross section here, intersection with the circle, Mohr circle, will be the pole. Right? So then if you plot the major principal plane and minor principal plane like this, from the original plane, and then this angle will tell you where the sigma 3f is applied, because it's passing the sigma 3f. And from here, when you plot the line parallel to the line from the OP to the sigma 1f, and this angle will tell you where the sigma 1f is applied. So in this plane, you have sigma 1f acting as a normal stress, and in this plane, sigma 3f is acting as a normal stress. So in both here and here, there's no shear stress by definition. When you look at the initial, when you compare this initial condition to the failure condition, then you can see that the principal plane has changed. So you have a rotation of principal plane during the shearing. That's a very good observation, important observation. And at least 3 tests are required to obtain the strength parameter C and V to draw the straight line. And nominal area or the cross-sectional area of a sample that's under a stress changes as the horizontal displacement occurs. So you have to correct them. Advantage of this direct shear test is inexpensive and fast and simple, and it's very intuitive and good for dry soils. But disadvantages are it is difficult to control the drainage, so it's very difficult to saturate the soil or unsaturated, partially saturate the soil, and because there's no drainage line or keeping the moisture inside the soil constantly. And failure plane is forced to be horizontal, but in situ field it may be a different angle. And stress concentration at the boundary is when you have this kind of rectangular shear box, you have the stress concentration at the corner here. And because of the failure of the shear force applied here, you have a more stress concentrated at the edge near the boundary. And lastly, you have a rotation of the principal plane and stresses, which will not occur in the field, which may not occur in the field. Okay. So then in the next page, we are going to talk about the shear behavior of dense soil and coarse soil. Dense soil and the loose soil, sorry. Dense soil, we can draw and idealize the soil packing like this. And in loose soil, we may have simple cubic packing. So simple cubic packing, and this is called a tetrahedral packing. So then let's imagine that we are shearing it in this direction. Oh, sorry. This direction, and here, and here. So what will happen with in terms of the particle movement? So if we take this one only, when we apply the force, this particle will climb up the next particle, right? So then, how about the volume change? So volume will increase so that we can call it the dilation or the volume expansion, right? But in the case we have a loose soil like this, and when we shear it, then the particle will go down to find the better space. So then volume will contract. So here, the dense soil, when you shear the dense soil, as the displacement increases, the void ratio goes up. So density goes down. But here in the loose soil, as the displacement or the shear displacement increases, void ratio goes down and the density increases. And this one is called a shear strain softening behavior. And this is called a strain hardening behavior. Okay. What about the stress strain curve? Yeah. So this is delta, and this is the shear stress. Then in the shear, the dense soil, you have this kind of a post-peak behavior. As the normal stress increases, sigma 1 and 3, sigma n2, sigma n1. And the volume change behavior will be like this. When the normal stress is sigma n3. So here, sigma n1 is the biggest, sigma n2 is the next, and sigma n3 is the smallest. So as shearing, the particle will try to dilate, so the volume will goes up. But as the normal stress increases, the dilation will be suppressed, so it will be like this. So greater stress greater normal stress reduces volume expansion or the volume dilation. Okay. And when you plot the shear behavior in the tau and delta space, so displacement, it will be like this. So sigma n3, sigma n2, and sigma n1. So as you go up, it's higher normal stress. Normal stress. And for the volume change, because it tries to contract, so it will go down like this. And because the normal stress is bigger, so they will contract more and more. Sigma n3, sigma n2, and sigma n1. And the example of this kind of soil is for the dense soil, it's dense sand. When you shear the dense sand, it will show this kind of a post-peak behavior and the strain softening behavior. Here, loose sand. And think about the clay. OC clay shows this kind of a strain softening behavior and dilation behavior. And NC clay shows the contractive behavior. drawing this called the dilated behavior. Good. Thank you. And we'll talk about and go through this example together in the Tuesday lecture.